I am going to introduce signal processing and machine learning automated evaluation of phrenic nerve affectation by cardiac stimulation. Cryo-ablation is a common procedure used in hospital to eliminate certain arrhythmias such as atrial fibrillation. Although this procedure is sufficiently proven, it sometimes involves treatment in areas close to the phrenic nerve, with the subsequent risk of later damage to the aforementioned nerve. To assess phrenic nerve activity, a stimulus must be applied in close proximity to the muscle. Currently, to avoid this damage, clinical practice incorporates manual safety protocols during ablation. Nevertheless, manual evaluation introduced a level of subjectivity. This study proposed the development of an automatic method to objectively evaluate phrenic nerve conduction throughout the cryo-ablation procedure, mitigating the risks of the eventual deterioration. The dataset used in this study consists of 10 cases involving ablation procedure for atrial fibrillation at the Virgen de la Risaca University Clinical Hospital in Murcia, Spain. Signal recordings were conducted during phrenic nerve stimulation in two distinct scenarios, with activation capture and without activation capture. Activation capture involved placing a sensor in the muscle to detect phrenic nerve activity, while the non-capture scenario positioned the sensor in areas unrelated to the phrenic nerve, enabling the acquisition of electrocardiographic reference signal unaffected by the phrenic nerve. The study encompassed four main phases: pre-processing, template construction, template characterization, and classification. The primary focus was on analyzing the surface electrocardiogram signal to detect and isolate nerve stimulation from the PQRST complex, as can observe in Figure 1. Subsequently, a delineation process was applied to obtain statistically the noise stimulation templates for precise analysis in each case. In the third phase, stimulation templates were quantitatively characterized conforming to clinical standards. By comparing capture and no-capture scenarios, the study determined whether muscle activity had been effectively activated under various condition tests. The study ends by proposing the use of linear support vector machine as a tool to categorize the two different options. Initial tests identified the first peak in the template as likely an artifact representing the impulse itself due to its synchronism and linear response to amplitude changes. Conversely, the second peak exhibited a non-linear response and consistent shape, indicating its association with phrenic nerve muscle activity, consistent with prior research. Experiments and measurements conducted in both scenarios comparing muscle activity amplitudes, with a specific focus on the difference in amplitude of the second peak, as shown in Table 1. Similar amplitude variation in both peaks during muscle activity capture suggested phrenic nerve involvement in the first peak. In cases without nerve capture, the second peak remained, confirming the presence of the initial stimulus artifact, as demonstrated in Figure 2A and B. By comparing results from both scenarios, the study could evaluate and quantify phrenic nerve muscle activity during stimulation. Achieving 100% of accuracy in detecting phrenic nerve activity in these datasets support the hypothesis of stabilizing an automated and unbiased protocol for measuring phrenic nerve muscle activity and its potential deterioration due to cryo-ablation conducted in this proximity.